好，我们开始上课。上课之前，我们说一下期中考试的时间和地点。我们是10月31号随堂考试，是半开卷考试，时间就是按课堂时间，从上课到下课，跟我们平时的时间一样，中间不休息。半开卷的意思是，大家可以带一张 A4 纸，一张 A4 纸，必须带。随便你怎么理解了。好，关于期中考试有没有什么问题？好，没有问题，我们就抓紧时间上课。So last time we introduced Wigner rules. This was developed to compute the time-altered provision function. In particular, we took the approach with the name, the so-called Schwinger-Dyson equation. So we use the Schwinger-Dyson equation. And as you can see, the advantage of this approach is quite clear. It's, first of all, the equation itself is a non-perturbable. As you can see, if you perform this calculation, I insert some third functions and replace the third function by range function and do perturbative expansion with the small copy, meaning the copy content is very small. And up to some order, you can approximate some correlators by the free field result. Then you can iteratively using this approach to do the perturbation calculation. So we are not going to simultaneously also using other approaches because we don't. I think we don't have much time. We need to cover many topics. So I suggest to you to do yourself. Derive precisely the same family rules, rather by using some other approach like a Hamiltonian approach, which was actually written in many textbooks. You can read yourself. But the final result will be the same. Okay. So we successfully obtained the so-called position space family rules. And in particular, there is a diagram or there is a figure to capture this long formula. Okay, we can basically follow the result and draw this figure for each term. Okay, and even including this combination rules. So, yeah, you can basically translate everything into a figure. Okay? And so the lesson is universally, if you next time, if someone give you a problem, you can even try to just draw the figures and follow the figures, write down the result. Okay? That's the advantage of Wigner rules. for example, we learned that there are building blocks for Feynman rules. For instance, we can just draw some building blocks. So, say if I have external points, then just draw some lines like this. We can have some other x2. We can also draw some y x2. Such lines, right? We associate each line a propagator. We denote by d1x dy2. We can also have following which interaction your theory carries. Okay? We can also have some other building blocks. For example, something like this: a three vortex. If the theory has a 3 phi interaction. Okay. You Lagrange, you also have such kind of structure, and for each such kind of vertex, we should assign a coupling constant to it. Okay? Coupling constant times ai, also times I. If you want to follow, just follow the diagram to write down the result for the formulas. And by using such kind of building blocks, right? Depending on which problem the setting is given, see which kind of correlating function you want to compute. That kind of input will determine such kind of x1 or x2. Okay? You get just draw the diagram, and with all the possible building blocks, try to contract, form, complete diagram. The point is we should sum over all the diagrams. Sum of all diagrams, okay? With all the lines contracted and all the vertices integrated over, okay? Because this kind of vertex is not given; it's something you created, okay? So you have to integrate over that kind of position. And we also mentioned if the correlation function is about say in such kind of vertex structure, if the three lines represent the same field without the distinguish, okay? For example, five cubic field. If the three lines represent the same field, there's possibly a symmetry factor, eventually will be divided by symmetry factor. Yeah, that's all we have to do. Okay, of course, I throw away some details. Basically, here we have to make sure all the lines contracted and the vertices integrated over. Yeah, this is so-called efficient space neighborhoods. Yeah, yeah. I also mentioned where this symmetry factor comes from. So basically, there's also a simple way of easier shortcut. Just read off symmetry factor. And we have a diagram with a vertex, and you can possibly permute some of the lines. Okay. Then if you realize that the diagram does not change, it means you need a two-factor overcome. Okay. You just divide all these overcoming factors. You can find out the correct result. Okay. So in the end of last time, we also mentioned the so-called momentum space invariance. Okay. Because we know by following the LSD, we can connect the time-ordered correlation function in position space to the amplitude or S matrix element. Okay, by LSD formula. Then we showed one very simple, extremely simple example last time. For such kind of diagram, you can indeed evaluate or calculate this amplitude from this correlation function. Eventually, we end up to some result like I equals to minus t squared over 2 integral over k, four-dimensional momentum, and then I p I minus k square plus epsilon. Okay, this is the result. We just honestly following LSZ from the position space result. Okay, we can derive this one. Okay, but the meaning of this IM compared with the position space Caudry function is changed, right? But the diagram is still the diagram because diagram is just the representation. Okay, it doesn't really mean that there is a particle and it can only go in that way. It's not. Okay, it's just a diagram to represent the formulas. Okay, it helps you to simplify understanding because there's a simple diagram. You just think of all the structure included in this diagram. Okay. So the meaning of this one is really, it really means there's input momentum particle and there's output momentum particle, okay? And there's a non-trivial intermediate process. And what are the probabilities? Or what are the amplitudes, okay? That's the meaning of the IM. Indeed, you can see it's a function. It's a function of PI. Because momentum conservation, PI is also equal to PF. So this is the input momentum, output momentum, okay? The point is we can, okay, this is the understanding of this is pretty simple. I think there's an incoming particle and there's out come particle. Because there's an interaction, okay? Interaction in the intermediate time, so there is non-trivial amplitude, okay? And the point is we also mentioned through all these steps, eventually we get some simple formula or result for the amplitude associated with such kind of diagram. Then we can just summarize to directly associate this result to this diagram. Okay, that's the point. This is so-called. We can also establish the momentum space. Yeah, we don't need to, we don't need to every time to go back to using LSD. Okay, we can just throw away the intermediate step. Just once given such a diagram, you can always just immediately write down the result. Yeah, this is not difficult at all, right? We also mentioned last time. You can see the rule can be summarized immediately. It basically says that all the internal lines we have to write down, for all the internal lines, we have to write down I over P squared minus M squared plus adaptation. Okay? All the internal line. Internal means what? It's not connected with the external points, right? Some internal line. Okay? And for each vertex, we have to put a factor I times the coupling constant as before, and possibly also divide by symmetry factor. And furthermore, what about the external lines? For external lines, we don't associate any probability, so no probability. Reason we already explained last time. Because LSD essentially did the job to cancel those propagators, right? From position space to momentum space. There is possibly an integral over some momentum, okay? Some momentum. The point is momentum. So the question is which kind of momentum you should integrate over, right? Now, there is an easy way to read off this one, to figure out it. You just first demand that the momentum is always conserved. At each vertex. Okay? Remember that If you still remember the process, we derived such kind of momentum space result last time. You still remember that? Then you realize, okay, this is not surprising at all, right? Remember that? Because we do free expansion for each propagator, including the external line and internal lines. Remember that? Then we integrate the x or y first. Okay? Those kind of integration immediately give a Wigner function. That's the meaning of that one is nothing but for at each vertex, the momentum is conserved. Okay? This statement is equivalent to the statement at position space. You have to integrate over all the internal points. Okay? Or vertex. Okay? That's the same equivalent statement. So after this one, then if I hand you a diagram, you can just treat all the external momentum input. Okay? Input means someone give you. You don't need to divide or find it or figure out. You don't need to do anything. Okay? Then you try to demand the momentum conservation at each vertex. After that, you try to see whether there's still some undetermined momentum. Okay? If everything is determined, of course, everything is determined. You don't need to integrate over anything. Okay? You don't need to do that. So the point is, after this step, you can try to find whether there are still some undetermined momentum. If there is, then it means you have to integrate over the remaining undetermined momentum. Okay? It's very simple, right? See, last time we already showed these steps. Let's say, yeah, it's not too serious. Just make or later when we talk about Fermat, a bit more careful. But for this diagram, we can just think because we assign this pi to the x1, so we put x1 here. So anyway, so we assign the input momentum in this way. So there's input momentum. Say you think about that there's input momentum, then there will be a k, right? If there will be a k, then for conservation reason, then there will be a pi minus k here, right? You see, then they meet together and become the pi or pi. That's it. Okay. You can think it this way. Then this means that there is an undetermined momentum, which is k. Okay, k is a free or undetermined momentum. You have to integrate over k. Okay. Then you just assign the propagators and integrate over k. Put carefully the coupling constant for each vertex. Okay, because each one contributes Ig and divided by symmetry factor. In this case, is 2. Then that's the exact result. This is the result for I. So do you have any questions for momentum space Feynman rules? Of course, we just draw a super simple example, right? This is not even it's not really like a collider, okay? It's not even a collider, it's just super simple. It's only a single particle in and a single particle out, okay? But there's a non-trivial amplitude. But typically, people are talking about 2 by 2 to 2, okay? 2 to 2 means really there's either the scattering, right? 2 comes in and 2 out. 2 to 2. But this is 1 to 1, okay? It's called 1 to 1. In order to illustrate all the calculations in detail, we choose this super simple example. So you may complain this is too simple, okay? What about a more general example, or a typical one? So let's give you some comments, remarks for such kind of momentum space Feynman rules before we go to the typical 2 to 2 scattering example. So the remarks is about some spectral structure. So for the disconnected, then you might wonder, a curious person, you wonder what if the diagram, the graphs are disconnected? do I mean by disconnected? Disconnected means we showed some, this kind of diagram you see they are connected, right? They're connected. Disconnected means disconnected. Okay. For example, you might have some diagram looks like this. It doesn't really matter. It's up to your convention, which side is in, which is out. For example, you might have some diagram that is disconnected, meaning that they may separated into two, for example, or even higher, 3, 4. This is called a disconnected. Okay, there's no connection between these two. But still, you can draw such kind of diagram, right? Right? For example, last time in the position space, we already saw some examples, right? You can do. There's no one forbidden you to do that, of course. Because the only thing we care about is the input and the input data, right? If you just formally think about these are the input, these are the input, these are the output, then this is certainly one process. You have to count, okay? There's no point for that. There's no question for that one. But how to understand this kind of disconnected diagram, okay? So you can easily convince yourself for such kind of graph or diagrams, scattering amplitude. Just factorize. Okay? Factorize means what? Factorize means you just separately count in this one, you get the amplitude, and count this one, you get amplitude. You just times it. Take a product with the factorize. Okay? Don't confuse with the sum. Okay? Last time we saw that all the possible diagrams, the relation between them is there's a sum, right? Remember that? But this kind of still belongs to a big diagram. Okay, that's the point. But the relation between them is disconnected. If such kind of graph happens, you can easily convince yourself scattering amplitude or the IM, even final IM is just a factorized. Basically, it means that you can do individual. You first do for this one and then this one. Okay. Because of this, so do we really need to consider such kind of disconnected graphs? Think about it for a few seconds. Okay. We need to do that. Actually, we don't need to do that in practice. Why? Because such kind of diagram must belong to a small number of particles scattered, right? Right? It's not the first time it shows up in the bigger number of particles scattered, like 3 to 3. Okay? My point is this diagram must contribute to or already contributed to 2 to 2. Okay? That's the point. Okay. So in the 2 to 2 counting, you have to take into that account, right? So you already computed that one for some other problem setting. That's the point. Okay. So in practice, because of that, in practice we can just always only compute connected diagrams. Okay. Yeah, that's one remark. Right? Because this is not the first time that this kind of diagram contribute. So I can design, if I'm experimenting, I can design my problem setting, I can mirror. Okay? Instead of mirror 3 to 3, I can first mirror 2 to 2, right? I can first mirror 2 to 2. So I just avoid such kind of problem. That's the point. Okay? Yeah, that's just a remark. It's not quite serious subtlety. It's just terminology. Depends on how you design your problem. Okay, how you design your problem. Now, as we mentioned, now let's take 2 to 2 to try to study the momentum space. Feynman rules, because we already know now the momentum space Feynman rules. We don't need to do rederive or the detailed calculations. Just try to use the rules to get the result. So how to apply the momentum space Feynman rules to counting the scattering? Let's take one example, 2 to 2. Again, we consider the theory or the interaction term we considered last time, which is the pi-cubic theory. Okay? We add this interaction to the free Lagrange. Okay? Consider such kind of pi-cubic theory. Then, since the problem, the setting is 2 to 2 scattering, so how to count in the scattering amplitude for 2 to 2 in such pi-cubic theory? So up to G square order, you can easily convince yourself, the diagram may contribute to the trace. For instance, this is P1. This is the input. Right? We consider P1 and P2 are the input momentum. Okay? And input momentum. For instance, we can make an error. Below this is input. Okay? This is my input momentum. And this P3 and the P4 are the output. Okay? You can easily draw a diagram like this one. Right? So you can see this is a typical diagram to contribute to G square order. See that? Because there are two vertices, right? And there is the two vertices. This is 2 to 2, and each vertex contributes 1 G factor. So this is the typical G square order contribution diagram. Okay? You cannot draw more, like some loops that in the intermediate channel, otherwise go to higher order. We want to just stay in the G square order. Okay? So this is the diagram. But if you are careful enough, this is not the only diagram. Okay? This is not the only diagram. Okay? You should always keep in mind that the problem setting goes in the following way. You should consider all the possible diagrams, okay, to fit with this given data, input data. Okay? These data are only about the such kind of, these are the only input data. Okay? Only this P1, P2, P3, P4. For any diagram fit into this given data, it should come. That's the logic. Okay? You should not throw away anything. So what are the possible other diagrams? For instance, you can easily convince yourself that one more goes in this way. So this is P1, P2, P3, and P4. Okay? This is E, R. Okay? See? You see, this diagram also fits with this input data. You see? Only the central structure is different, right? You see? Up to this central structure. The others are so-called given data. You see? All others are the same. You see? No problem, right? So this diagram also contributes to this 2 to 2 scattering, right? There's even one more. Still, I don't change the input given data. I just try to draw the diagram. Right? You see, I faithfully respect the Feynman rules, just to draw all the possible diagrams, right? See, because I only count the G square order. For each diagram, there are 2 vertices, right? Okay, here also there are 2 vertices. Okay, it's nothing happened here, so I draw some such kind of figure. So nothing happened here, just one line is going this way, one line going they don't touch each other. Okay? See? There's no all the three diagrams are equally important. You see? You cannot say, okay, this is your favorite, this is not your favorite. They're equally important. Because all the diagrams are perfectly respect the Feynman rules. Okay? And they belong to the same order. It fits with the given data, which is 2 to 2 scale. Right? And then the point is these three are different, right? You cannot see they are the same, right? There's no point to say they are the same. You see? But the structure is different. Right? Now, so we should that which means we should add up these three diagrams. Okay? Add up these three diagrams. So we should add. So then what is the result, right? Sometimes we denote let's denote the amplitude for the first diagram as for example I and S. The second denoted I and T. Third denoted I and U. Okay? I and U. Just denote the amplitude, right? Amplitude is IM. Now, just following the momentum space Feynman rules, we have to sum up. So this is the I. We have to add up these three and read off the results. Now let's do it honestly, just to try to apply the momentum space Feynman rules. Okay? Let's say this is in, this is in. If this is the direction, the intermediate momentum will certainly be 1 plus 2, right? Because it's a conservative, right? It's conservative. For this vertex is conservative. Output must be 1 plus P2. Okay. So see, if I denote this is the direction, momentum direction, then this is in. This is also in. But this one belongs to the, because of the conservation of this vertex. Is P1 minus P3, right? See? P1 minus P3. So for this one, if I denote the direction in this way, this is following the same rule. It's P1 is in, this is out, this is also out. So this must be P1 minus P4. Okay? So the difference for these three diagrams is the intermediate channel momentum is different. Okay? Then certainly following the Feynman rules, the amplitude will be different, right? So this back, justify the back. These three diagrams are different. Okay? They're not the same. So you cannot see them the same. Okay? The formula, represent formula is different. So just honestly following the rules, what we get is the IG times. For each vertex, we associate the IG, factor IG. Okay, factor IG. And for each internal lines, we associate the propagator, which is I over for the first diagram, for example, P1 plus P2 propagator minus the M squared plus epsilon. Okay. Okay. So this is the result for the first diagram. Okay. There's no symmetry factor at all here. You cannot predict anything because these are the given things. Okay. It's not a probability. So you don't need to do that. So that's it. This is the result. And for the other two diagrams, we just check out because this is basically only this piece is different. All others are the same. Okay. Only this piece is different. All others are the same. So, so these are the minus IT squared, P1 minus P3 squared minus M squared epsilon. And the third diagram result is minus IT squared, P1 minus P4 squared minus M squared plus epsilon. Okay, that's it. So I finished this. Counting. I get the result for this 2 to 2 scalar amplitude if you only care about the d square order, okay, for the phi cubic theorem, that's it. It's very simple, right? Now we are not only satisfied by obtaining this result. We also want to understand better deeply what this final result shows. Why this is interesting. Okay. So introduce a bit notation. Usually, I already give a subscript, so-called S and T and U, a subscript index for the amplitude. So this is for the reason usually people just redefine, make another notation for this P1 plus P2 square. Just redefine this factor as S, okay? And redefine this one U, and redefine this one, sorry, this is T, and redefine this one as U. That's why I call it, sometimes we call it, this is the S channel, and this is the T channel, and this is the U channel, okay? This is the U channel, okay? That's because of this one. Just a name, okay? Because this is a definition. If you redefine, make a short notation, just redefine this one with into S. This is T. This is U. We can rename this using a short name again. This we call the S channel, T channel, U channel. Okay. Okay. It's just no mysterious. It's just a redefinition. And you can easily check. If you did such kind of redefinition, you can easily check S plus T plus U will be the sum of the external particle mass. Okay. The J means all the external. Because this notation is specially prepared for the 222 spectrum. And you can always do this. Okay. It's the experimental 222. You always have two input, okay, momentum data, two output momentum data. All these are given data, okay? Okay? Your job is to counting the intermediate process, right? That's the usual setting of the problem. Then you can easily check this is true. This J over the how many external? In this case, J over from 1 to 4. Okay. In this case, if all the external particles carry the same mass, then this is 4m squared. Okay. It's about counting the external particle mass squared sum together. Okay. This is the S plus T plus U. The convenience of such such redefinition provided you can rewrite this total amplitude in terms of S, T, and U variables, right? S and T and U variables, right? There's no confusion about that. First term is the S minus M squared plus epsilon. This is T minus M squared plus epsilon. This is U minus M squared plus epsilon. Okay? Since S and T and U are Lorentz invariant, and you can express your final result, IM, in terms of S and T and U variable, which means you obtain a result as a form of Lorentz invariant variables. Okay? This kind of result will not depend on which frame you're working on. You can choose whatever you want, you like. Then you get such kind of result. This is universal result. It's also applicable to other frames because the S and T and U are Lorentz invariant. Okay. This is the advantage, one advantage for such kind of formula. So basically, once you know a result in one frame, you know the result in other frames. Okay? This is the good point about this new notation. As you can see, these are the input given data. So this looks a constraint because S plus T plus U to sum together equals to this one. Okay? It just says that even though you can express your final amplitude result in terms of S and T and U, but S and T and U are not all independent variables, right? There's a constraint. If you want, you can use this constraint just replace your U, right? Right? Your U will be equals to this one, you see, subtract S and T, right? Then your final result can be only in terms of variables S and T. Okay? Is that clear? By the way, to show this constraint, you should, of course, you should use momentum conservation, as you can see. Because this is P1, P2, P3, P4. Again, they are not all independent. There's a conservation. There's a conservation. The conservation, there are few conservations, right? For each row type, there's a conservation, okay? By using that, you can eventually show this constraint. Anyway, we express our variables, momentum variables, in terms of new STU variables, with in mind that there is one constraint for S and T and U. Then basically, there are two independent channel momentum. Okay, if you want, we can always choose S and T. Okay. But it doesn't really matter up to notation. So why this is interesting? From this example, I want to also make another remark, which is up to now we took basically two examples. One is this one, the other is this 2, 2, 2. Okay. Even though these are very simple examples, we can try to summarize some lessons from this exercise. Another point is, even though up to now we explicitly computed the S matrix or amplitude, scatter amplitude, by using such a diagram, and the diagram comes from the perturbative expansion, right? So if you only focus on a particular diagram, for sure your result will be only perturbative result up to some order. Okay. For instance, this is only for the G² order. Okay. We didn't claim anything about higher orders. You want to claim high orders, you have to do something more. For instance, this we also only claim up to G² order. Okay. All these are perturbative results. But this doesn't mean S matrix can be only worked out at the perturbative level. Okay. Conceptually, if you are a careful person, you should realize that the S matrix is actually conceptually is defined non-perturbatively. It's not only perturbative. It means what? For instance, 2 to 2. Okay. The S matrix conceptually is defined, for example, for 2 to 2 process, is entire non-perturbative language. Okay, right? Which means that I can define the S matrix to contain all the possible processes. Okay, not necessarily only include a few perturbative diagrams. Okay, for example. Yeah, this figure is very convenient to understand that. Okay, so usually people denote it to concept doesn't matter which in which out. So this is in, this is out. Okay. Okay. So the S matrix is well defined for a given theory. S matrix is well defined as we introduced a few weeks ago. If the only condition is asymptotically there is a free particle state, then it's enough to define S matrix. Remember that? Okay. All the intermediate time window we allow the many complicated things. Okay. You can imagine how complicated it can be. Okay. It doesn't matter. S matrix only care about the asymptotic state. If the asymptotic state is well defined, S matrix can be very fast. That means S metric is conceptually can define in this way. We don't care the black box here. Okay, this can be an arbitrary black box, complicated process. This essentially means S metric is conceptually defined not only perturbative but also non-perturbative. Okay, it's just a matter of calculation, your technology. Okay. Up to now, we don't have much technology, but we do have some, but we don't have many advanced technology to deal with the non-perturbative S matrix. Okay. So it's only a calculation difficulty. It's not a conceptual problem. Okay. So S matrix is defined. Indeed, there's a it can also non-perturbative. Okay. It's also non-perturbative. So why I want to mention this in this course, because indeed recently there is a hot topic for the so-called S matrix bootstrap that is precisely want to deal with the non-perturbative calculation of such kind of S matrix. Okay. So suppose this is a little away from the what we learned so far, but let me just mention in case some of you might be interested in, because this is a new field, okay? It's under development, so it's worth to mention. So the so-called S matrix bootstrap says that let's forget about all the Feynman diagram counting, okay? Let's just try to guess or ask ourselves whether we can, from the beginning, to raise the problem and then to solve the problem in completely non-perturbative way, okay? For instance, since S matrix conceptually is well defined in non-perturbative way, I can just try to work out all the constraints for S matrix, okay? For instance, some constraints we already mentioned, right? So what are the constraints? For instance, number one, we mentioned the S matrix should be unitary, right? Remember that? So S matrix should be unitary, okay? This is the basic property for S matrix, okay? And from that 2 to 2 together, we can also try to observe some other properties for S matrix. For example, here, you can see this final result, if you just replace this U by that constraint, this final result is completely symmetric if you exchange S and T. Okay? You realize that? If you exchange S and T, the result does not change. Okay? So this is another property called crossing symmetry. Okay? Now, if you're a careful person, you also realize the S matrix might have some more good properties. For example, look at this kind of result. We always include the I epsilon deformation. You see? Yeah, this is worth to emphasize. Yeah, because following the rules, we said we have to assign such kind of structure to the internal lines. Now, for these internal lines, as you can solve from that 2 to 2 example, this momentum, this form momentum, is not necessarily to be on share. Okay? You see? Because it's not the external lines, right? If it's external lines, then they represent a free particle state. It must be on share, right? But this is the internal lines, not necessarily to be on share. But after that, you can try to design P1 and P2 to make this approach, maybe approach to some on share point, right? Because this P basically can change depending on the external momentum. Okay, and this mass is the internal channel mass. Anyway, I'm just trying to say that this I epsilon is very important if this momentum if the momentum P squared goes to M squared. Okay, as we learned from the Feynman propagator, I epsilon is designed to clarify the detailed structure of the poles, okay? Right? To make sure you did the correct control integral. That's the whole point of the action. Okay? This, in some sense, already tell you that when you consider amplitude as a function of momentum, you have to go to the complex plane, momentum plane, okay? You shouldn't restrict yourself too much. Say, momentum are always real variables. See that? Because we already employ the techniques, right? That's essentially the techniques. Remember that? When we try to use, take use of the control integral, we already mentioned we consider this P0, right? This P0 is not only a real variable, but a complex one, right? Otherwise, there's no I epsilon, right? I suggest already you extend your momentum to a complex. So, in a general way, the amplitude can be viewed as a function of some complex momentum. Okay, that's one another lesson. So this raises another property of amplitude, which is so-called analytic. So the amplitude has analyticity property, or is an analytic function of the momentum up to some poles. Okay. And actually, the poles always has a very sharp physical meanings. So this is another good property of the S matrix. So of course, there could be some more higher constraints. The point is, if I know all the constraints about some object, we can just try to deduce or guess the object. Okay. If you're lucky, the answer could be unique. Then you got it. Okay. In a non-perturbative way. That's the idea. So do you have any question? We basically finished the discussion for the momentum space Feynman rules. Do you have any question? Yes. Yes. Yeah, you can do different choice. The property I mentioned does not depend on the choice, but you can do different choice. Ah, okay, good. Yeah, right. I didn't explain it. The point is, you see, when someone tells you the values of kind of P1, P2, P3, P4, it cannot free, right? It's not a definite data. There's no God-given data for those momentum. Depends on frame. If you choose a center mass, for example, you get some sample, possibly sample formula for this momentum. But you can shift to other frames, right? The momentum will be changed, right? So there is some kind of ambiguity or frame dependence here. I'm trying to redefine this, repackage this momentum in terms of S and T and U. S and T and U comes from the square. It's just a Lorentz invariant. Lorentz invariant means the value does not change when you change frame. Any other question? Okay. So we finished basically the Feynman rules, including both position space and momentum space, for a simple theory, which is scalar theory. So up to now, we only talk about scalars, both free and interacting case. But fortunately, we get a little bit of a feeling about what's the difference between a free theory and interacting theory, how to use Feynman rules to capture and do some calculations. So the next step, we'll just try to broaden the scope to think different types of fields. Okay, not only scalar fields. We also want to touch our real world. Okay, but our real world, the typical quantum fields is the photon. Okay, it's the photon. Okay, or electron. So we want to really touch those real objects. Okay. So we have to develop our framework or discussion for quantum field theory. We have to extend them to other fields, okay, or other particles with different spins. Scalar has a spin 0, right? Okay. But thanks to the discovery of Higgs, we really find for the first time, okay, find the elementary scalar field, okay. In our world, so now we can see that scalar fields is also real quantum fields in elementary level. But now we want to move to the other particles of quantum fields. So the next step, or the main topic of today, we are going to discuss the spin 1 fields, which is the photon, which is associated with the particle photon and age invariance. Okay, that's the main topic. But before that, we want to systematically understand. We don't want to blindly go there, from here to there, and then jump into there. To just talk about just different fields or particles, right? So what is the point? What is the unified framework? Why we have to go to particles with such spin to that spin? How to classify? In other words, how to classify different particles or different fields? Okay. This is a bit discussion actually. Yeah, let me quickly sketch the idea and the most famous result to classify different particles and different fields. Right? Then it's not surprising. You can imagine that all these classifications comes from symmetries. Okay. So, yeah, so let's go back a little bit to talk about particles and fields. So how to really understand, rigorously, systematically classify both particles and fields, and also in relation between them, right? At some point we mentioned in the beginning, quantum fields is different. It's very different from usual quantum mechanics in a sense. It's infinite degrees of freedom. That's true. Okay. But on the other hand, sometimes we also mention that, for instance, we can talk about some simple quantum state even in the framework of quantum field, right? For example, in the free scalar case, if we act the vacuum by a simple AP diagram, okay, we can just get a perfectly good state, okay, up to some little bit issue about normalization, but it's a good state, okay. So we can find such kind of state, quantum state, even in the quantum field theory, okay. So there is some way to understand how to. That essentially means we should be able to embed particles to fields. Okay, right? That's a two philosophy, right? That's a two philosophy. First of all, if you just jump into fields to look back at particles, we see, okay, there are a lot of degrees of freedom, infinite degrees of freedom, many particles, things like that. But we can also see, okay, in this very complicated work, we can just try to find some simple particle space. That should be okay. So we can embed particles into the fields. Okay. So how to systematically talk about this one is that this should all due to the symmetry. Or our word, our real word, is a symmetry word. Okay? So why I say so? As mentioned some time ago, the flat space of Minkowski space-time has a symmetry. In group theory language, we're going to mathematically make the symmetry very clear. We call that this is the form of the Poincare group. Because in mathematics, we use group theory to symmetry, particular symmetry. But this is physically, this is nothing but our real world symmetry. Space-time symmetry. Okay? We're talking about the symmetries, right? We should be familiar with this one. By that, I really mean the space-time. We have translation invariance, translation, symmetry. We have rotations. We have also boost. Okay, rotation plus boost forms Lorentz group. Combined with translation, additionally there are 4 translations. Okay? Combined with 4 additional translations, entirely, totally they form the Poincare group. Okay? So the Poincare group comes from the Lorentz group plus translations. Yeah, this is the isometry. This is the isometry. Sometimes we call this is the isometry, but it's just a name. Right? We know what is Lorentz group, right? Lorentz transformation forms the Lorentz group. Now translation forms another groups. Combined together, we form a larger group that we call the Poincare group. Is that okay? Yeah, we try to use some kind of physical word to describe them without going into much mathematical details. Okay. So the important point here is this is really a God-given symmetry. Everything should respect because this is our real-world structure. On the other hand, we also know our world is filled by different particles. Different means different types of different particles. So now we should try to understand the framework. Why we can embed the particle as a quantum state into the space-time, which has a nice symmetry structure. Okay? Okay? So the best way to do this is combined with quantum state, right? Just think about that there is a state describe the particle. For that, we know, for that purpose, we know we have to characterize a particular type of particle by different quantum numbers, right? For instance, momentum. Remember that? in the first lecture, we used the P momentum eigenstate, right? That essentially means some particular free particle state must carry a particular momentum, right? Which is P, because you active a P dagger, okay? Every ground state, you have to carry a particular P. That's one quantum number for that particular state, okay? For instance, we also know another quantum number, which is mass, right? Very fortunately, mass is also Lorentz invariant. I mean, rest mass, okay? Rest mass is P squared, so it's Lorentz invariant, right? So you no matter you choose which frame, okay, or change the momentum, the mass is invariant. So that looks a very good quantum number for that quantum state, okay? So yeah, so summarize the different quantum state to describe the particles have different quantum numbers. And some of the quantum numbers might depend on very heavily depend on the particular frame. For instance, momentum, you can change it easily, right? You can change it. Say, for the same particle, I can change its momentum, okay? For instance, I can just switch to another frame. The momentum we'll observe will be different, okay? This way, maybe we can change the momentum. And some other quantity maybe rely on this one, it will also not change. And but fortunately, there are some other very good quantum numbers will not change at all. So of course, those are quantum numbers that we call they are mostly invariant. So from our experience, we want to take use of these invariant quantum numbers to capture the particles. Yeah, very often we use those good ones. So with this understanding, as said, how to build up to classify different particle states to fit with space-time symmetry. What we can think about is in an abstract way, we can think about the quantum state as denoted by different quantum numbers. And they transform under Poincare transformation or Lorentz transformation. Okay? So a particle, you can take it as this is as a definition of particle, quantum particle. A particle can be defined as a set of states that transform among themselves under Poincare, because Poincare is the complete assembly with all the space-time transformation. Okay. For example, Lorentz transformation. This is where we should be familiar with, right? With Lorentz transformation, we basically change the momentum. Okay, change the momentum of the particle state. Okay. So if you think about it, this is the transformation in the Hilbert space. Okay. This means the transformation will send one state to another state. Okay. For example, formally, if I denote using this very abstract state to denote a particle state, then under the Poincare transformation, they would use P. This P is not the physical conserved. The other charge momentum is not. Is here I really denote it means a general Poincare transformation. Okay. Okay. Maybe I should use a U instead of P. UP is better. Yeah, formula. So everything's okay. So this says that a particle state can transform under Poincare transformation, right? For instance, one typical example is Lorentz transformation. That's what we learned in the first few lectures. Because of this one, clearly you represent this Poincare group, right? Because this is the represent the Poincare transformation. This transformation forms a group. You can think about U is a matrix. Okay. Okay. U is a matrix. It represents the Poincare group. Simultaneously, this vector or this kind of quantum state psi or acetol state, we also call this is a representation of the group. The group means Poincare group, right? Right? It depends on how you think it, right? Because that U is acting on some object, okay? There's kind of one-to-one correspondence, right? Starting from some psi, okay? Right? For each U, I can associate with another new psi. So in that sense, the psi also represents the group, right? Okay? If you know some knowledge about group theory, that will not be surprising. For example, to be more precisely, for example, I think this is enough. This should be clear. So, if there's no subset of a state transform only among themselves, we call such kind of representation is irreducible. Okay, this is also the same definition of the group theory language irreducible representation, right? Right? You see, reducible means what? Means there are many states, right? Basically, in Hilbert space, this should be belong to some very huge Hilbert space, right? In Hilbert space, there are many vectors, okay? There are many vectors, okay? Simply, you can consider all the transformation as kind of rotations, okay? This is rotated from this direction to that direction, okay? And quite often there is the space, of course, are many, and even the dimension of the representation is also to be very high. Okay. Okay. The reducible means that there's some particular subset, which is a subset of the entire state. Under the transformation, they just play the game with themselves. Okay. It's a small team. Okay. They don't touch the others. Okay. If such kind of thing happens, we call the representation given by those states is reducible. Okay? If you can never find a subset of the state, they just transform among themselves, which essentially means there's no small team play with themselves. Then you call such kind of representation are irreducible. Okay, irreducible. Yeah, this is as well a little bit a physical understanding without a rigorous mass clarification, but hopefully it's okay. Yeah, so why I'm trying to clarify this, I'm trying to show the particle or the particle state, if they represent this Poincare group, and it should also satisfy the unitary property. And what I mean is, the physical observable or the interesting observable is often given by some inner product or overlap between states. Okay? Right? Because state itself is not an observable, right? It's not physical observable. So quite often we are interested in some inner product, for example, arbitrary two. They're not a component, but just two typical different states, right? We care about such kind of overlap because this kind of thing could be related to physical observable, right? Now, under the P or U, under the U transformation over there, you can easily check after the transformation, these two states after the same transformation will both change, and eventually, for instance, I denote this with M. Then after the transformation, this M prime, it goes to M prime, and M prime will become the side 1, U, tiger, U, side 2. Okay? And also we know such kind of amplitude given by this kind of overlap cannot depend on the U transformation. Basically, they should be invariant under concurrent. For instance, one example is the free particle overlap. Okay, easily check this one. Free particle. Remember that? You have two states. For instance, let me raise another example. Because we are familiar with Lorentz transformation, so one example will be the X and the P state overlap. Remember that? We specifically computing. And then eventually we get the result is e to the I P dot X. Remember that? Because this is P dot X. This is Lorentz invariant, right? So we justify this X state overlap with P state with Lorentz invariant. Okay? So I want to promote that example for more general, as a more general fact. So for such kind of overlap, it always should satisfy under the U transformation. Okay? You think about the U, for example, as a Lorentz transformation. Okay? They should not change, meaning that they should be equal to the original value. This immediately tells you that all the U transformations should be unitary. Okay, should be unitary. This also means that we call such kind of representation. Either you think about it represented by U, or you think about it represented by psi. We call such kind of representation it's a unitary representation. Okay. So, yeah, this is a very crucial condition to allow a famous physicist called Wigner to classify all the different representations for the Poincare group. Okay, it's called the Wigner theorem. This is, you can think about this a little bit warm up to introduce which kind of problem we're now talking about. Okay? Now I'm telling you a very sharp theorem. We're not going to prove it. Okay? If you want to do it yourself, we're not going to prove it. I will just show the final result. The final result is very sharp. So Wigner famously showed that all the irreducible unitary representation are classified by two simple numbers, which one is mass, another is the spin. S. J. Here J is not the level current, it's just the spin of the particle. Okay. This is the result. It's coming from the this is some representation theory. You can think about this as the mass theory. Okay. Just coming from this theory. Because Poincare group is well defined. Now we can classify the different representations. Okay. You restrict to only this irreducible and also unitary ones. Okay. Then there is a sharp classification of all this. Okay. This work is due to Wigner. So what is the result? The result is quite simple, right? It just says, okay, all these unitary representations are classified M and J. This is the mass result, but for us, this is quite useful to classify different particle states, you see? Because the whole point is the quantum state describe the particle should fit with this representation, right? Because we are staying in the Poincare, Minkowski space-time. We should fit with the Poincare symmetry. We should unitary irreducibly represent this Poincare transformation. Okay? Yeah, if there is a good, well-defined particle state. Yeah, that's the whole point. Right? Then you ask, unitary, we already spent a few minutes to explain why unitary, right? Why unitary? Simply because the overlap or the amplitude shouldn't change under the transformation. Okay? So you could immediately deduce U dagger U equals to 1. This means the unitary. Okay? This means the representation is unitary. Okay? Now, why is irreducible? Can anyone guess why is irreducible? It's very simple, right? Because we are now talking about elementary particles. Okay? An elementary particle you can think about, you cannot be divided further, right? Think that way? Right? That's the reason why we are careful about reducible. If it's reducible, you might think about there's a small subset, but not touch with others on the order transformation. It might describe something else with some composite particle, whatever object, but not an elementary particle, right? So, two numbers, that's very good if we only care about the result. For the two numbers, we restrict it to m should be greater or equal to 0 and also real, and j should also greater or equal to 0. But again, due to this mass theorem, can only take the half integers. Something like 0, half, 1, 3 half. Only 0 or half integers. Okay? The two numbers. Now, not only this one, for sure, the theorem carries more. The theorem basically classifies all the particles. This is one. Elementary one. Theorem also claimed that if you only consider positive spin, meaning j greater than 0, then for each momentum means each value of the momentum right? Because we already mentioned the different momentum basically can capture different states, right? Momentum can change, okay? The momentum can change. The Shen theorem also says that for each value of momentum, if we consider its own shell relation, we will have p squared equals to m squared for sure. Because it's relativistic particle. And there are 2j plus 1 independent states. If m is also positive. There are only two states if m equals 0. Okay? It looks a little bit complicated. Just trying to categorize what this message, what this information says. Okay? It just says that j equals 0 might be a little bit special. Okay? Does not fit into this category. Just make an exception. Okay? Now consider general positive j. Okay? Consider positive speed. Right? This is compare with this, only make this j equals 0 is a special case. For all these positive j's, for each momentum means now given a momentum, the fixed momentum for the particle state. Okay, meaning that the particle state, think about the free particle state, that the momentum is given. But even for the fixed given momentum, if the spin is not 0, for the massive particles, okay? So this is called massive. For the massive particles, depending on the j, there's always a 2j plus 1 physical state, independent state. You can think about this is the usually we call the degrees of freedom. Okay? Degrees of freedom for the particle. For massive particles. Okay? Is that okay? Now, what is the typical example? You know, you should check against your familiar knowledge about the elementary particles, right? What are your most familiar massive particles? That's right. So electron. So for electron, what is J? What is the J for electron? Yeah, half, right? J is half. So 2J plus 1 is 2, right? It's 2, right? That's why we call the electron has 2 degrees freedom associated with speed. Okay? Okay? Up and down, right? That's a 2 degrees freedom for the electron. Now, if for massless particles, whatever J you have, you can only have 2 independent states. Okay? Now, again, check your familiar examples. What is your familiar example? Photon, graviton. Okay? What is the spin for photon? What is the spin for photon? That's right, 1. But it doesn't matter, right? One is for all the massless particles, there are can only 2 physics states. The same thing is true for graviton, right? So graviton, even though the spin is 2, but since this massless, there could be only 2 degrees of freedom, or 2 independent states for given momentum. Okay, for given momentum. So this is the reason we are going to justify it soon, but this is essentially the reason why we call for photon. Okay, but photon is our most familiar electromagnetic field in our real world, right? Photon is the elementary particle, which is the particle. Okay, for the electromagnetic field, or for quantizing the electromagnetic field. That's essentially the reason why we saw photon has 2 polarization directions for the given momentum. Okay, that's what you should learn already from your electrodynamics. Okay. But again, yeah, but let's finish this one. So what if J equals 0? Then J equals 0, there's only one state. So each P is different. This is both true for massless. Okay. Again, I'm not going to prove this one, but if you want, you can find a proof in one word, what you want. See a proof. So remember that this is purely coming from representation theory of the Poincare group, okay? It looks like a pure mass theorem, but indeed it's quite useful. Just sharply tells you that what are all the possible physical particle state, okay, for elementary particles. Right? It's very useful. You can just remember the conclusion, right? And then try to check consistent with your other analysis or your other knowledge from somewhere else, right? Keep this in mind, always keeping this in mind, and you can check against with other conclusions. Yeah. Let's have a break. OK，积完了之后，再 Q 掉一个，三个 Q 三个，这是 P 图。K K。那这个积分 K， 我看这个 K 没有意义，到底然后你说的 K 直接单个就可以了，不会交出去。对，第二呢，你设在一个积分 K 也没有一个需求，只是我们在我们可以是顺序的。没有想，你这个深圳，这个样。A 和 B 这个页面对。 Okay, let's continue. So we introduced a very important result due to Wigner in 1939. Basically classify all the possible physical states for the elementary particles. Now, what is the next? Okay, this is just tells you about the possible quantum numbers for the particle states. Okay, it doesn't tell you more information about the quantum fields. Okay, so the next question is how to embed a certain particle or particle state into a full quantum field theory. Okay, right? So particle and the field, how to embed. Next question will be how to embed. In the question, there's a question here. Even though you know all this, that's very good. It basically tells you about the degrees of freedom for all the possible physical elementary particles. But next question is how to embed particle. This is all about only about particles, right? How to embed particles into fields. Okay? A priori, you know a spin zero particle doesn't mean you know a scalar theory, right? In principle, they are different concepts. But from our experience, we also know the related, right? The related, the directly related. So the question is how to embed a particle into the fields. So in other words, why we can use scalar, okay, to represent, to describe a spin zero particle, right? This is the question. So again, we should explore more about the relation between particles and fields. We can classify this one by representation theory with Wigner. We want to understand how to embed the particle into fields. Okay. So the question is, what are the Lagranges for fields that contain particles with single speed? Before talk about the theory, including many different particles with different speed, let's first focus on one typical type of particle, only for single speed. Okay. When we talk about spin zero, we don't touch others. We talk about spin one, we also just focus on spin one. Okay. Then at least the minimum question you can ask is, what are the theories? What are the field theories which can contain the particles with a single speed? Okay. Now we also, some point, we also realized that the unitarity for the representation from the representation theory, we already get the feeling that we know that the unitarity will be very important. It's not an arbitrary representation. It should be unitary representation. Okay, unitary is very important. It should be unitary. Now, of course, we should justify whether the theory is unitary or not if we know the full quantum theory of some field theory. Okay, means we know the full quantum field theory. Okay, but before you quantize a field, from our experience, we first establish the Lagrange, meaning that for the classical fields. Okay? Then, how do you know your classical field theory could potentially be unitary or not? Okay, that's the question. Because unitary is about using state to justify. We always talk about unitary. Unitary means unitary evolution, meaning the transform of state or evolve of state. That's the easiest language to talk about unitary. If you don't have the notion of state, okay, which is true in the classical level, we don't have the notion of state. Then how can we talk about unitary? Right? That's also a question to ask yourself. So in the classical level, indeed there is such kind of issue, but in the classical level, we instead of talking about the unitarity or demanding unitarity for some theory, because now we want to construct a theory, some theory, right? Step by step. First the classical level and then quantize it for all the different spin particles. Okay, that's our task. But we want to make sure that theory it's better to be unitary. But again, as I said, in the classical level, we don't have a good language to justify unitarity. Instead, we justify something else. That something else is the energy bound from below. Or you can think that this just means the positivity of the energy up to shift. Because you can always shift the reference of your noise energy to define maybe this is your zero energy state. So yeah, so energy is bounded from below. I'm not claiming this too because there are the different framework claim, okay, or yeah, a statement. This is for quantum. This is at this moment we can talk about only a classical level. But I want to claim that if the energy is not bounded from below, okay, otherwise the theory is unlikely to be unitary, okay. That's I do want to claim. The reason is very simple. If even in classical level the energy is not bounded from below, meaning that you allow the let's say infinitely active energy, okay? If you allow that one, when you quantize the system, because we know in quantum mechanics, different energy levels they can jump, okay? They can jump. Quantum mechanics, if you have different energy levels, okay, there's a certain transition probability, right? From one energy level to another energy level, okay? Which essentially means if the energy is not bounded from below, whatever quantization procedure you take, you will eventually arrive at the conclusion that there does not exist a good ground state. Very clear? That's very clear, right? You always jump to the next energy state, okay? That makes you don't have a stable ground state, which essentially means if you don't have ground state, you need to make the theory thick. Right? It's always decay to the smaller energy state. So that kind of theory, we don't think that can be unitary. Okay, this is another angle to see that. I'm not claiming these two are completely equivalent because they are different level of statement. But I'm trying to say even at the classical level, the minimum demanding is that energy should be bounded from below. Otherwise, after you quantize it, it's unlikely to be unitary. So let's go back a little bit to check what we are trying to do, which is embed the particle in fields. The simplest example will be the spin zero, right? Will be the spin zero. Will be the spin zero. Let's check a little bit. Go back to the scalar field. So for spin 0, due to Wigner, what are the degrees of freedom for spin 0? 3. Only one state, right? Only one state, or only one degree of freedom. Now, if you want to construct some field theory to represent the only one degree of freedom, what is your economic choice? Of course, a scalar field, right? A scalar field. So 1 degree of freedom. And we choose a scalar field. Now we also know that the simplest free scalar field theory is the Lagrangian is given by this simple form. Okay, and in particular, we also actually worked this out some time ago. Let me just write it again. We also know that the energy density or Hamiltonian density is given by the this one dot minus L. Okay, this is the PQ dot minus L. Okay, which is giving you H. Okay, now let's use the epsilon. This is the energy density, which knows this one. You can just evaluate this guy, and you immediately realize that this is a half partial t. We write it in terms of component terms. This is nothing but this one. Okay. Okay, you can justify it immediately because these are all the square plus. Okay. These are all the square plus. Okay. And they are real things. So real things, you take a square and you take a plus. This must be greater or equal to 0. Okay. You see? Indeed, here energy. This is the energy. Okay. The basic meaning of epsilon is energy. Is energy or energy density. Okay. The difference between energy and energy density is actual volume. Okay. So this is the true energy. So this is bounded from below, justified back. This theory is good because the energy is bounded from below. Okay. Now this is the simplest example. Now we want to go to what if we today the main topic is we want to go to spin 1. Okay. So for spin 1, there are different multiple choice, right? For spin 1 means j equals to 1. It means j equals to 0. Okay. For j equals to 1, we have different category. Depends on you talk about the massive or massless particle. Okay. For massive particle, what are the degrees of freedom for j equals to 1? What are the number of degrees of freedom? 3, right? It's 2j plus 1. Okay. For m equals to 0, whatever j it is, it has to be 2. Okay. So these are the different categories, different cases. So in principle, you can try one by one. First, for instance, you can try this one. You can try to embed a massive spin 1 particle into fields. Just try to construct the field theory. Okay, the field theory includes 3 degrees of freedom. So what is the minimal choice to represent the 3 degrees of freedom? Can you guess? First thing you may come in mind, it could be used as some vector field, right? Because vector field has 4 components, okay? Right? You can embed 3 to 4, right? Because 4 is the closest number to 3, above 3, okay? So you can try to imagine that you might build up some theory, take a mu as your elementary field, write down some Lagrangian to represent the massive spin 1. Theory. Indeed, this in history, this was indeed achieved. We know this can be done. Okay, because this is just a massive, some kind of massive gauge. Sorry, a massive vector field. Okay. Now, since time is limited, let's focus on this one. because this is our real world, right? As we mentioned, our real world photon is nothing but the particle carries J equal to 1 and no mass, 0 mass. Okay? And due to Wigner, we know already there are only 2 independent degrees of freedom. Now, how to achieve this one? How to embed this photon into a field theory? We don't need to do step by step, right? Or too much guesswork because we already know the answer, right? Right? So what is the answer? What is the answer for this one? It's Maxwell's theory, right? It's Maxwell's field, okay? It's nothing but Maxwell's field, Maxwell's theory. Because we know Maxwell's theory is the correct field theory to describe photon, okay? Which is nothing but electromagnetic fields, right? That's our real world. Now let's talk about this one. So let's review a little bit, or recall a little bit of basic knowledge about Maxwell's theory. It should be very familiar to you. Say Maxwell's equations, okay? As said, we already know the answer for that purpose, how to embed that J equal to 1, M equal to 0 particle into the field theory. We already know the answer. The answer is the amount is given by minus quarter at mu u. Okay? We already know the answer, right? Now, F mu nu is defined by partial mu a mu minus partial mu a mu. Okay? Yeah, let's quickly review a little bit about this theory, okay? In order to establish clearly the connection and justify why there are 2 independent degrees of freedom. Okay? Is this too clear to you? Everyone know there are only 2 degrees of freedom for Maxwell's theory? Know it? Don't know it? Okay. Yeah. So then let's work it out. So the equation motion from the Lagrangian is, as you can work out, you just take the standard procedure to work it out. This will equal to minus partial mu after mu to be equal to 0. Okay? This was your homework exercise. Last week. Okay. This is the equation motion, right? This is the equation motion. Now to connect with the Maxwell's equation, you were familiar before. We should really write this 4 vector A mu in terms of component, right? Because this is nothing but the scalar component of the potential. Like the potential together with the A hat, right? Right? This is what you learned in college physics, right? And the relation between the electric field and with this potential will be E equals minus gradient action phi minus partial A vector partial T, and B is the vorticity of this. Okay. Okay. This is a relation. I guess most of you will be most familiar with the Maxwell's equation written in terms of E and B, okay? But not with A or F, okay? Now let's just build out the relations. The relation given by this one. Okay? Now, so you can explicitly write the relation between F and E because of such kind of relation. You can explicitly write F and as E or B field. This is minus EX minus Y minus B. This is 0, 0, 0. This is B, this is minus B. This is minus BY. This is BX. Minus BX. Okay. The component of the F is nothing but the E or B. Okay. In terms of matrix, you can write it that way. These are the relations. These are the relations. Okay? Now, from equation 2, number 2, where's 2? From equation number 1, which is nothing but this equation, this is our equation motion derived from this Lagrangian. Following the standard procedure, we also know the F written in terms of E and B, so you can just plug in. Okay. Write down all the components. Write this in terms of, as component equations. Then you realize that equation motion will give you two pieces. One is the divergence of E equals 0. By the way, I threw away all the source terms, as you can see. Okay, here, because I will only at this moment I only want to talk about the Maxwell theory without source. Okay, without source. And partial E, partial T equals to vector cross B. Okay, this is from equation 1. You can easily check. Now, can anyone tell me what are there? We know there are 4 Maxwell equations. Additionally, there are 2 more. Okay, what are the 2 more equations? What are the 2 more equations? This is only 2. Where are the other 2s? You should be able to write down the other 2, by the way, right? And then think about where it comes from. Where it comes from? You know? Does anyone know? That's right. It comes from some identity where, by definition, F mu nu should automatically satisfy. Okay, because if you think about F mu nu, for example, in terms of this kind of 4x4 matrix, you should be able to observe some very special property, okay, of this F mu nu. What are the properties? This is anti-symmetric. See, this is anti-symmetric. You see, anti-symmetric means what? If you conjugate, if you transpose this matrix, you get a minus sign. See, for that reason, all the diagonal part is true, 0. Okay, this is an anti-symmetric matrix. You can also see from here. If you switch the mu and the mu, okay, you get a minus sign. This is an anti-symmetric matrix. The anti-symmetric component. And you can easily check yourself. There is a so-called identity with a validity. Identity called the Yankee identity. It's a length. Okay, Yankee identity goes this way. from the definition, you can check this is true. Okay? And furthermore, if you plug in this component, the E and the B field, into this identity, you get the other two Maxwell equations, which you are familiar with. Okay? So this is the connection. But we're not satisfied about this is just some kind of identification or rewrite what you already know in terms of some new notations. That's not a big deal, okay? So what we really want to do not only just rewrite something you already know, but to try to understand the physics in terms of these new A fields. Okay? For example, there's a famous property about the Maxwell's theory or Lagrangian, which is called the gauge symmetry. Okay? Even the Maxwell theory looks everybody should be familiar, okay? But actually, it's quite rich, okay? Especially when you quantize it, okay? It's far from trivial to understand completely the quantization of the Maxwell's fields. So even in the classical level, we can observe the gauge symmetry, which says that consider a transformation which send the A field goes to a mu x plus some derivative for some arbitrary scalar function, some arbitrary function lambda x. The lambda x can be arbitrary. You can easily check L or Lagrangian. L does not change. So under this transformation, L does not change. Right? You observe it, it's almost trivial, right? Right? Because F does not change. You see? You see it? Because lambda x is some function, you can exchange the derivatives, okay? If you shift this A by a partial, say partial nu of lambda x, then you exchange the derivative, which you take which derivative, it doesn't matter for lambda x, okay? Then these two shifts will be cancelled because of this structure, okay? So F does not change. So L is built from F, okay? So L will of course not change. Okay? So we observed quite an important structure, even though this theory looks simple, but there is an important transformation which preserves the Lagrangian, therefore preserve the action. Okay, because we learned a little bit about the global symmetry a few weeks ago. This is related but quite different things. Okay, so this is called we call such kind of property a gauge symmetry. And this can be easily justified because of F does not change. The gauge symmetry is different from global symmetry. We learned it before. Okay, what are the difference? What are the difference? What are the difference? Remember that? Previously, when we defined the global symmetry, we also using some parameters to penetrate the symmetry, even though there are different versions, like infinitesimal version or finite version. Okay, but in both cases, the parameter represented the symmetry transformation is not space-time dependent. But here you see that different. So you can think about this symmetry, because these are the new object to purely capture this transformation. You can think this lambda x is the object that represents the symmetry here. And importantly, lambda x depends on x, which is different from what we learned before. We didn't touch anything looks like this before. Whenever we talk about global symmetry, it's not like such kind of feature. Okay? But the common point is to both preserve the Lagrangian or action. Okay, that's the common point. But the crucial difference is one, in the case of global symmetry, is the parameter which parameterizes the transformation. There's no x dependence, but now there is the x dependence. Because of this leads to completely different physical interpretations. Okay, completely different physical interpretations. We know previously, when there is a global symmetry, we say that there is a physical transformation associated with that symmetry. Okay, because all the symmetry is represented by the transformations. Okay, for global ones, the symmetry transformation is really physical, meaning that it sends some physical state to another physical state. For instance, I translate it from here to here. Okay, this is the perfectly good for quantum state. This is a perfectly good transformation. Before the transformation and after transformation, they're both physical states, right? Clear? That's for the global symmetry, but the interpretation for here, the gauge symmetry, is completely different. So gauge symmetry does not relate to different physical states, rather it implies a redundant degrees of freedom. Yeah, this is a little bit of jump. In order to fully understand it takes time, but it's okay. Don't worry too much. As you learn, maybe after 10 years, you can get a more better understanding. But just go along with it. Okay, the gauge theory is deep and subtle, and there is also under development. It's not really fully established. Crystal clear. A chapter. So this gauge symmetry implies the redundant degrees of freedom. This means what? This means rather instead of related to physics state, just show up some equivalence in some space. Okay. So the question is how to understand this redundance. Okay? Let me try to sketch what do I mean by that. Okay? So how to understand this the gauge redundance? I'm just trying to roughly picturize what I mean. By redundance, I really mean that this kind of transformation consider start from some, okay, I wouldn't say start from, consider a different lambda. You choose a different lambda, okay? Let's say I start from some A field, okay, mathematically. I can start from some A field just to plug in a particular lambda, because lambda can arbitrary function, right? You choose whatever you want. Lambda x can be x squared or polynomial function, whatever you want, okay? You already justified it. It's a good transformation to preserve the Lagrangian, right? So when you transform it, it means you insert a particular lambda, right? You transform A field, right? Right? Then, we know we can also perform many steps, okay? Because it's a transformation. I can do one step transformation and then second and the third. And then all these transformations eventually form an orbit, okay? Some path, okay, orbit. So if you write the orbit in terms of lines, it can represent it in this way. Okay? This line just means that they connect any point, all the points in this line corresponding to a particular lambda. Okay? Is that clear? Okay. And there could be many orbits. Okay, many orbits. This is just, don't worry too much. This is just a schematic picture. So these are called the gauge orbit. The point is why I call the something redundant. Okay. The point is the entire line only represents one to a physics state. Okay. Suppose you transform starting from some physics state. Under this transformation, that state might change a little bit mathematically. Okay. But the point is, since this is a gauge symmetry, all this you transform some point from some point then to some point. The point is all these points represent the equivalent physics state. Okay. And a different point is just manifest some mathematical difference. It's not a physical difference. Okay? But that's just a word, some statement. We are going to justify this statement in the following discussions. But here is just a sketch, the pictures. So that's why we say sometimes we have to fix this ambiguity, or you can think in terms of ambiguity. Okay, ambiguity. Okay. With our physical world, in order to capture some physical object, there are many different ways. Okay. Sometimes there is ambiguity. Ambiguity means that there's mathematically there's many ways to capture the same object. Okay. But all these mathematical quantity describe the same physical object. This is called ambiguity. You can also think about this orbit presents some ambiguities. There's only one physical state. Okay. Now, to fix this looks weird, right? You go to, for instance, you have some very simple degrees of freedom, very simple physics system. You try to introduce a lot of variables. Like, okay, it's describe a simple one, but a lot of things are redundant. Okay, redundant means, or you can think it's unphysical. It's not necessary. Right? It's not the most economical way. But so far, we don't have much better choice. We have to stay in this framework. But we have to understand what are the redundancies or ambiguities. So in order to fix these ambiguities, we just cut or choose a section, meaning that we already claimed that each orbit represents a single physical state. So we just pick up only one point for each orbit, okay? Meaning that we choose a section in this way. This is often called a gauge fixing. Okay, so I understand that this is a little bit, if it's your first time to hear about this, it's a little bit fancy. We're trying to explain to you what's the meaning of this gauge redundancy. Okay, for example, you can also understand it in the traditional way. Okay, I know most of you guys are very comfortable with everything expressed in terms of E and B. Right? You're very familiar with, right? Because E and B are observed fields, right? You can measure it, of course, it's physics, right? There's no redundancy or unphysical things at all. Okay? So everything is physical, okay? If you express in terms of E and B. You also understand it in that way, okay? In that sense, we know there's a direct relation between E, B, and F. So in that sense, you can think about this F mu nu are physical variables, okay? Indeed, they are, right? Right? Now, F mu nu is the physical variables. We also justified that kind of transformation completely preserve F mu nu, right? So you can get some feeling about that? Meaning that kind of transformation will completely give the same physical variables FC. Okay? This is essentially indicate that lambda penetrates some redundancy. Okay? Some unnecessary redundant unphysical transformations or descriptions. That's what I mean by this kind of thing. Okay. Don't take too seriously about that figure. We're going to more details to understand this better. So the next thing, we are going to justify why the Wigner's result about photon. Why Maxwell field has only 2 independent degrees of freedom, not 4. Okay, mathematically this is not clear, right? Because I use a mu field to represent Maxwell field. You see? I use a mu to represent this M. Okay. See, a mu has 4 index. Naively, you might say, okay, there are 4 degrees of freedom. It's like a couple of scalar field. You have 2 scalar fields and you have 2 degrees of freedom, 3 and 3, 4. Okay, but that's not true. Okay, that's heavily related to this gauge redundancy. Okay? This gauge redundancy suggests already implies that there are some unnecessary degrees of freedom which are not physical, which makes this confusing here. Okay, why it's 2, not 4. Okay, now we have to go from 4 to 2. Okay, justify it. Why? Okay. So is the question clear? Now we are going to justify, or we're going to justify why Maxwell's field is only 2 degrees, not 4. Okay. I said that it's not completely fruitful a chapter about gauge theory in particular after you consider quantization. You can develop your own ideas, for example. See, I mentioned some claim here. You might just challenge it. See, why don't you bother with this A field, right? Someone will just stand up and say, I can only restrict myself to talk about a theory in terms of E and B. That's okay, okay? Because we know E and B are more physical variables, right? So one terminology maybe for you is that I shouldn't bother with A. I should forget about A, okay? I should always write everything in terms of E and B. Yeah, that's one philosophy. You can try in that way, okay? Okay, you can try that way, okay? Okay, so here, let me go with this A field, which means the first thing we have to work it out is the equation motion for A, right? Because we think A is the elementary field here. Now we already write it down the equation motion, which is nothing but partial F equals to 0. Now if you want to write this in terms of A field, you just write explicitly, okay? Because F is defined by A, partial A, okay? Then you just plug in to write down this equation motion in terms of A. Yeah, so now in terms of component, I want to write it more explicit way, which is in terms of components, meaning I distinguish the time component and the special part. Then this is the partial J. J means run over from 1 to 3, not 0, okay? Without time direction. Square A 0 plus partial E, partial J, AJ equals 0. Since I decompose everything in terms of component, I basically throw away the philosophy of the contract up or down index, because everything is a component. There's no meaning to talk about now the covariant index, okay? Because this is a component field. So the meaning should be clear, okay? So here I write this JJ, because that means the repeated index again summed over, but we know that summed over about the component fractions. There are 2 pieces, of course, right? Because F mu nu in terms of partial A because this equation is essentially four equations. You see, with mu index is summed over, right? Right. A nu can run from 0, 1, 2, 3, right? So this equation becomes four equations in terms of components. So you can write down basically. So the first one comes from, we take nu equals to 0, okay? You can check yourself. Now, second one, we have to, we can take a nu equals to j, run over from 1 to 3, okay? Then this will be the component equations. As I said, all the repeated index are also summed over. But this, both I and j are just run over from 1 to 3. Now, I mentioned in order to continue, we have to, as said, there is a huge gauge redundancy, which is represented by that kind of transformation. And we have to somehow do this gauge fixing. So in terms of equations, which kind of gauge fixing we choose? Of course, the gauge fixing is not unique. Okay, it's not unique in a sense. You can pick up such kind of section. You can also pick up another section, right? Because the section pick up a particular section means gauge fixing. After pick up this fiction, you basically cleared all this redundancy, right? Because this line represents an equivalent class for a single state. Okay. So the gauge fixing condition is not unique, but we have to choose one, right, in order to make everything more physical. Okay. Otherwise, we already understand there is a redundancy, which is not physical. So which gauge fixing we choose? We choose a particular gauge fixing called a Coulomb gauge. So Coulomb gauge, in terms of equations, is nothing but partial j and ij. Aj equals 0. Or if you want, in your middle school notation, this will be the partial dot. Okay. That is the same thing, right? This is called a Coulomb gauge. It's called a Coulomb gauge. Then you can check yourself. There are two components of the equation motion. In particular, you can check after plugging in this gauge fixing condition, the equation motion 3 will become simply a partial j a square a0 equals 0. See? Equation 3 will become this one, right? Because this is 0, right? 0. But only left with this one equals 0. Okay? This means what? A0 is also 5, right? In your familiar notation, it's 5, right? It's 5. It's time component of your vector potential. We also said that now we are free of the source. In the system, there's no source, right? So the right hand side is 0, right? The right hand side is 0, right? So in a system without source, you consider the A0 as a. If you consider A0 as a component field, A0 is a field, by the way. Okay, it's a field. If you consider as a component, a zero component of the A mu field, this is the equation motion, because we always impose the fall-off boundary conditions for all the fields, as we mentioned some time ago. We always think that the fields are die-off at infinite far. Okay. So in the flat space, those are essentially the boundary conditions. So as you might learn from your college physics, right, there's a unique solution if you set a very established boundary conditions for such kind of equations, right? So So the only solution is for the trivial form of boundary condition is A0 equals to 0 because of such kind of equation motion without source. Okay. So you can simply take A0 as is actually equals to 0 because of this. Is it clear? Now we have a couple of equations, right? This is our gauge fixing equation. We should always keep in mind. Okay? Because those conditions take the job to kill the unphysical degrees of freedom. In that sense, it's extremely important. It's a priori important. Okay? After you do whatever analysis about the system, you should impose that equation first. Okay? It's kill the unphysical things. So now we have a couple constraints or equations we should keep in mind. These are the conclusions we already derived. Okay, to study the system further. Now plug in this kind of conditions into the both equation motions, all the equation motions. What do you get? This kills this term, right? This by gauge fixing is 0, right? Is it clear? The only thing left over is this part. Okay? Equals to 0. Okay. The only thing left over is AI box AI equals to 0. Under this coolant gauge. So, if this is true, this means that this is the remaining or final, after a bit of analysis, this is the final equation motion, which is left, okay? Which is left. Now, are you satisfied, or do you think we already finished? We can make our conclusion already, or not really yet. This is the equation we arrived so far. Now, you might just stick to this equation and say, okay, I reduced the whole system or more complicated equation down to here. Okay. Now I run from 1 to 3. Now this looks like a 3 vector, right? Looks like a 3 vector, right? Because this is the equation motion already. You can take I equals to 1 or 2 or 3. It gives you 3 equations, okay? Like a 3 mass links together, okay? You might think, okay, our system, there are only 3 degrees of freedom is left. Is that true? What do you think? By what? From where? Right, that's right. So it's all quite correct. We shouldn't, as we emphasize always, we shouldn't forget this condition. Okay. Here, this is because this is gauge fixing. Here is like a God-given equation. You should always take it. So this is, in a sense, this is characterized the dynamics only with this kind of condition. Okay. So basically, this condition kills further 1 degree of freedom. Okay. Okay. Because we said A0 equals 0 is solved. Okay, it's a solution. Okay. Now you repackage summarize everything. You realize, okay, this is my equation motion, but there's one additional constraint here. The constraint will take the job to kill 1 degree of freedom. Then we will achieve 3 minus 1 equals to 2. Okay. This is a rough analysis, but indeed this can be made more precise. Yeah, let me take 1 more minute to see how it happens. For example, yeah, you can analysis both this equation motion with this gauge condition a more precise way. For example, we try to do the Fourier expansion. That's what we did for scalar field. Okay, that's what we did for scalar field. Now, if you plug in this field, this field, we already throw away A0 component because A0 was killed. Okay, to set to 0 forever. Okay, you can safely forget it. The only left over is A vector. Okay. Now, this is the equation motion. Follow the procedure as what we did for scalar field. We want to find some form in this momentum space. Okay, to solve this equation motion. Remember that. And eventually do a canonical quantization, right? Remember that? Let's do the similar thing. You plug in this one, you can easily check yourself. This is a solution for equation motion, provided this p, the square equals 0. Okay? Remember that? Because it's a 3-dimensional integral, the fourth component of the momentum is not independent. Is determined by this p. Okay, this makes this 3-dimensional p integral very defined. Okay, and indeed you can check it. This is the solution for the equation motion because the box acting on this one is amount to take a twice derivative with the x, you get the p square, and the point is p square equals 0. Okay, you see. Now we shouldn't forget again the gauge condition. So you plug in this form, is plugged into the gauge condition. From here, you get something interesting, which is the epsilon vector dot p is 0. Okay. This said what? This said basically the epsilon vector and the p vector are orthogonal. Okay, because the dot is 0, right? They're orthogonal. It transfers to each other. Okay, because the dot is 0. Now. Actually, I guess you already learned your electrodynamics. This epsilon vector takes the duty to characterize the polarization, the so-called polarization vector. Okay. So indeed, let's fix p. See, let's fix p. You can find the epsilon is orthogonal to the p, which means that for your electromagnetic wave, this momentum direction is the propagating direction. Okay, that polarization should be transferred to the momentum direction. Okay, so this epsilon is so-called polarization vector. So you can solve it. More than that, it can be make very precisely. You can actually solve this one, meaning that you can solve it. Let's say I can choose, for example, I can choose a frame. I can choose a frame which is the z, x, y, z, right? Which is the set my momentum, propagating momentum along the z-axis, which means that in terms of 4-vector language, we choose a frame to let my momentum p equals to E0, 0, P, such kind of components, right? If I choose such kind of P, you can find that there are two independent solutions for your epsilon. For example, epsilon 1 is equals to 0, 1, 0, 0, and epsilon 2 equals to 0, 0, 1, 0. Right? Because we know there are two independent polarization directions. A general polarization vector is a linear combination of two independent bases, right? Right? Because the transverse plane is two-dimensional, or transverse to the p, right? Transverse to the p, which means there are two-dimensional space, vector space. You can always choose two independent epsilons, and to think about a general epsilon is a linear combination of these two. Okay? Now I promote this three vector up to 4. You see, this is trivial, right? Because I always said the 0 component is 0, right? This is 0 because A0 is 0, always 0, right? A0 is 0 in terms of the Fourier space is equivalent to say epsilon 0 is 0. Okay? So I always took that notation. In that sense, I can promote this both P and the epsilon up to the 4 dimension as a 4-dimensional vector. Okay? And that's a trigger promotion. You can do either way. I choose doing this way, so you can easily justify it. This relation means that for a given, let's say, such a simple P, I can find these two independent polarization vector. Easy. See? You can check it. This means you can work out the two independent polarization vector out of this equation. Okay? Out of this equation. This equation also satisfies P squared equals 0, right? It's coming from equation of motion. Okay? There are only two constraints here in the momentum space. Okay? So this is justified eventually. This is justified. Combined what you learn in your electrodynamics, this is justified. These two polarizations justified. There are 2 degrees of freedom. There are 2 degrees of freedom for the A field. You see? No more than that, right? 2 degrees of freedom. Okay. Yeah, so let's stop here. We'll continue next time. 这个没来的同学，你们把期中考试的信息转达一下。剩下2周我们就要考试了。